Hello everyone, I'm Francois and I work on the Keras team. And I'm going to be talking about TensorFlow Keras. So this talk will mix information about how to use the Keras API in TensorFlow and how the Keras API is implemented under the hood. So we'll cover an overview of the Keras architecture. We'll do a deep dive into the layer class and the model class. We'll have an overview of the functional API and the number of features that are specific to functional models. We'll look at how training and inference work. And finally, we look at custom losses and metrics. So this is the overview of the Keras architecture, all the different submodules and the different classes you should know about. The core of the Keras implementation is the engine module, which contains the layer class, the base layer class from which all layers inherit, as well as the network class, which is a specific kind of model. It's a directed acyclic graph of layers, as well as the model class, which basically takes the network class but adds training and evaluation and saving on top of it. And also the sequential class, which is, again, another type of model, which just wraps a list of layers. Then we have the layers module, where all the actual instances, usable instances of layers go. We have losses and metrics with a base class for each and a number of concrete instances that you can use in your models. We have callbacks, optimizers, regularizers, and constraints, which are much lighter modules. So in this presentation, we'll go mostly over what's going on in the engine module and also losses and metrics, not so much callbacks, optimizers, regularizers, and constraints. So in general, for any of these topics, you could easily do a 1-hour talk. So I'm just going to focus on the most important information. So let's start with the layer class. So the layer is the core abstraction in the Keras API. I think if you want to have a simple API, then you should have one abstraction that everything is centered on. And in the case of Keras, it's a layer. Everything in Keras pretty much is a layer or something that interacts closely with layers, like models are layers, for instance. So a layer has a lot of responsibilities, lots of built-in features. At its core, a layer is a container for some computation. So it's in charge of transforming a batch of inputs into a batch of outputs. Very importantly, this is batch-wise computation, meaning that you expect n samples as inputs, and you're going to be returning n output samples. And the computation should typically not see any interaction between samples. So it's meant to work with eager execution, also graph execution. All the built-in layers in Keras support both, but user-written layers could be only eager, potentially. We support having layers that have two different modes.
Does it mean that user-written layers can support eager and graph, or only eager?
Yes.
Yeah, okay.
That's right. And typically, most layers are going to be supporting both. If you only support eager, typically means that you're doing things that are impossible to express as graphs, such as recursive layers or tree LCM. So this is actually something we'll cover in this presentation. So yeah, so layers also support two modes, so a training mode and an inference mode, and you could do different things in each mode, which is something that the dropout layer or the batch normalization layer do. There's support for built-in masking, which is about specifying certain features or time steps in an input that you want to ignore. This is very useful in particular if you're doing sequence processing with sequences where you have padded time steps or where you have missing time steps. A layer is also a container for state, meaning variable. So in particular, a trainable state, the trainable weights of the layer, which is what parameterizes the computation of the layer and that you update during backpropagation, and the non-trainable weight, which could be anything else that is manually managed by the layer implementer. It's also potentially a container that you can use to track losses and metrics that you define on the fly during computation. This is something we'll cover in detail. Layers can also do a form of static type checking, so they can check. There's infrastructure that's built in to check the assumptions that the layer is making about its inputs, that we can raise nice and helpful error messages in case of user error. We support state freezing for layers, which is useful for things like fine-tuning and transfer learning and GANs. We have infrastructure for serializing and deserializing layers and saving and loading their state. We have an API that you can use to build directly acyclic graphs of layers. It's called the functional API. We will cover it in detail. And in the near future, layers will also have built-in support for mixed precision. So layers do lots of things. They don't do everything. They have some assumptions. They have some restrictions. In particular, gradients are not something that you specify on the layer. You cannot specify a custom backwards pass on the layer, but this is something we're actually considering adding potentially, something like a gradients method on the layer. So it's not currently a feature. They do not support most low-level considerations, such as device placement, for instance. They do not generally take into account distribution, so they do not include distribution-specific logic. That at least that should be true. In practice, it's almost true, so they are as distribution agnostic as possible. And very importantly, they only support batch-wise computation, meaning that anything a layer does should start with a tensor containing, or a nested structure of tensors containing n samples, and should output also n samples. That means, for instance, you're not going to do non-batch computation such as bucketing samples of the same length when you're doing time series processing. You're not going to process TF data sets with layers. You're not going to have layers that don't have an input or don't have an output outside of a very specific case, which is the input layer, which we will cover. So this is the most basic layer you could possibly write. It has a constructor in which you create two TF variables, and you say these variables are trainable, and you assign them as attributes on the layer. And then it has a call method, which essentially contains the batch of inputs to batch of outputs computation, in this case just Wx plus b. So what happens when you instantiate this layer is that it's going to create these two variables, set them as attributes, and they are automatically tracked into this list, trainable underscore weights, right? And when you call the layer using underscore call operator, it's just going to pass, so it's just going to defer to this call method. So in practice, most layers you're going to write are going to be a little bit more refined. They're going to look like this. So this is a lazy layer. So in the constructor, you do not create weights. And the reason you do not create weights is because you want to be able to instantiate your layer without knowing what the input shape is going to be. Whereas in the previous case here, so this is the previous slide, you had to pass the input dimension as a constructor argument. So in this case, you don't have to do this because you're going to create the state in a build method, which takes an input shape argument. And when you instantiate the layer, it does not have any weights. And when you call it for the first time, this underscore call operator is going to chain the build method that you have here and the call method. And in the build method, you see we use this add weight shortcut. So it's basically just a slightly shorter version of creating a variable and assigning it on the layer. Layers can also have non-trainable states. So trainable state is just variables that are tracked in trainable underscore weights. Non-trainable state is tracked in non-underscore trainable underscore weights. It's very simple. So in this layer, in the constructor, you create this self.total scalar variable that starts at 0. You specify it's non-trainable. And in the computation method, you just update this variable. And basically, you just keep track of the total sum of the inputs seen by this layer. So it's kind of a useless layer. And as you see, every time you call this layer, the value of this variable is being updated. Layers can be nested, so you can set layer instances as attributes to a layer, even if they're unbuilt, like here. And when you do that, the outer container, so in this case, the MLP block instance, is going to be keeping track of the trainable weights and non-trainable weights of the underlying layers. And all these layers, which in the constructor are unbuilt, are going to be built, so have their variables created the first time you call the outer instance. And this is the most basic way in which you can be using a layer. You would just instantiate it, grab some loss function, which could be anything, grab some optimizer, iterate over some data. So you have input data and targets, open a gradient tape, call the layer inside the gradient tape so that the operations done by the call method are recorded on the tape. Call your loss function to get some loss value, and then you use the tape and the loss value to retrieve the gradients of the trainable state of the layer. Then you apply these gradients. So this is a full end-to-end training loop. So by that point, you know about layers, which are containers for state and computation. You know about trainable state, non-trainable state. You know about nesting layers, and you know about training them, which is kind of loop. So typically you would put this part of the loop, like everything, starting with opening the gradient tape, ending with applying the gradients. You would put that in a tf function to get a graph execution and faster performance. So when you know all these things, you can use the Keras API to implement literally anything. However, it's going to be a fairly low-level way of implementing things. So by that point, you know everything, except you actually know nothing. So let's go further. One neat feature is that you can use layers to keep track of losses and also metrics that you define on the fly during computation. Let's say, for instance, with our linear layer, after we just compute Wx, we want to keep track, we want to add an activation loss on Wx, which is just going to be the sum of this output times. So it's not actually a great loss because it should probably be squared of a sum of the square instead of just sum, but whatever, times some factor, right? And when you have a layer like this, every time you call it, the scalar tensor that you added here in this add loss call is going to be tracked in this layer.losses list. And every time you call the layer, this gets reset. Right? When you have nested layers, and then the outer container is going to keep track of the losses of the inner layers. And you can call the inner layers multiple times. It's not going to reset the losses until you actually call the outer container. So the way you would use this feature is something like this. After you open your gradient tape and you call your layer and you compute the main loss value, you would add to this loss value the sum of the losses collected during the forward pass. So you can use this feature to do things like weight regularization, activity regularization, compute things like the KL divergence. So all kinds of losses that basically you are easier to compute when you have access to intermediate results in the.
Just a question. So if you have call add loss in a inner layer, is it call but that layer is contained in another layer? Does it call add loss on the outer layer too?
Yes. So so for instance, if linear layer had multiple layers inside it, when you retrieve, so this should be a linear layer that losses, not model losses, whatever. It's going to recursively retrieve all the losses, including the top-level losses.
So I guess my question is, does a layer know that it's being called
from inside another
That's
layer.
correct, meaning that when it's called from inside, you can call it multiple times. It's not going to reset the losses. The losses are only reset when you call the top-level container. So there is a call context thing.
Oh, I was expecting it to be reset every time you call it, but the parent's losses.
So if you do that, you could not share a layer that creates losses inside a bigger model.
But I mean, I guess I was thinking that the inner layer would reset, but the outer layer would not reset. So it would as long as all the inner layer losses are added to that layer.
So they're gathered on the fly. So that's not exactly how it works. But yeah. Anyway.
So how does the resetting happen? Can you explain?
Yeah, sure. Basically, you just it's called at the end of underscore call for the outer container, and it's called recursively. So it's going to clear the losses of all the inner layers. If you want to do it manually, all layers and models have a reset losses, I believe it's called, method that you can use to force clear all the losses. Which could happen, for instance, if you have multiple calls of the same model. Like I think potentially the GAN use case could be, anyway.
Sorry, so I didn't understand how reset losses is not called. How does a layer know that it's being called as from an outer layer?
In underscore call, there's basically a context manager that sort of says you're in underscore call, and so that's why sort of as you go down the line, if you're calling a layer that's already being called inside of another layer, it can use that context manager to know whether it's the top level call.
Okay.
So yeah, so layers also support serialization. So if you want to make a layer serializable, you just implement a getConfig method, which typically just packs the constructor arguments into a dictionary. And when you've implemented this getConfig method, you can serialize your layer as this static config dict, which is JSON serializable, and you can use it to reinstantiate the same layer. So this does not keep track of the state of the layer, meaning the value of the weights. So this is done separately. And so layers also support two modes, training mode and inference mode. If you want to use this feature, you would have a training argument in call. So this is a very simple example of a batch normalization layer, where when you're in training mode, you're going to be computing the mean and variance of the current batch, and you're going to use these statistics to normalize your inputs, and you're going to be updating the moving mean and variance on the layer, which are non-trainable weights here. And if you're in inference mode, you're just going to use the moving statistics to normalize your inputs. So now let's move on to the model class. So you saw in one of the previous examples that layers can be nested. If you just switch in this example from having the MLP class inherit from the model class instead of the layer class, then essentially nothing changes, except that now you have access to a training and evaluation and inference and saving API. So once you've inherited from model, you can do things like mlp.compile with an optimizer and the loss instance. Then you can call fit, which is going to automatically iterate over this data set and minimize this binary cross entropy from large its loss using the Adam optimizer. It's going to iterate 10 times over the data set. And you can also save the state of this model with this mlp.save method. So what's the difference between a layer and a model? In short, is that a model handles top-level functionality. So a model is a layer, so it does everything a layer does in terms of network construction. It also has this compile, fit, evaluate, and predict methods. It's about saving. So when you call save, that includes not only the configuration of the model, like the getConfig thing we saw previously, it also includes the state of the model, like the value of the weights. It also includes the optimizer that the model was compiled with, and the state of the optimizer. It also supports some basic forms of model summarization and visualization. I can call model summary, which is going to return a description of all the layers inside the model and the number of parameters that the model uses and so on. So in general, the layer class corresponds to what is usually referred to as a layer, like when you talk about a convolution layer, a recurrent layer, and so on. It can also be used to refer to as what is sometimes called a block, like a resonant block or an inception block. So layer is basically either a literal layer or a block in a bigger model. And the model is really like the top level thing, the outer thing, like what people refer to as a model or a network. So typically what you would do is use the layer class to define inner computation blocks and use the model class to define the one outer model, so the thing that you're actually going to be training and saving and exporting for production. So for instance, if you are working on a ResNet 50 model, you would probably have several ResNet blocks subclassing the layer class, and then you would combine them into one big subclass model on which you would be able to call compile and fit and save and so on. One feature that's specific to TensorFlow 2 that not many people know about is that by default, when you call compile and fit, you're going to be using graph execution because it's faster. However, if you want to execute your model eagerly, you can pass this run eagerly argument in compile. You can also just set it directly as an attribute on the model instance. So when you do that, all your call methods in the top level MLP model, and so all the inner layers are going to be executed eagerly. If you don't do this, then by default, we're going to be generating a graph function that does the computation, which is faster. So
before you go on, question, could you explain the sort of difference between compile and fit? Like what goes in compile and what goes in fit?
Right. So compile is about configuring the training process. So you specify which optimizer you want to use, you specify which loss you want to minimize, you specify which metrics you want to try, and anything else is going to modify the way the computation is done. That's going to modify the execution function, which is something we're going to go over in more detail. And in fit, you're passing the data itself and information about how you want this data to be processed, like how many times you want to iterate over the data, potentially the size of the batches you want to use to iterate over the data, which callbacks you want to be called at different stages of training, and so on. So it's configuration in compile and basically passing the data and related metadata in fit. So you typically compile your model once, but you might be calling fit multiple times.
So a way to think about it is that if in TF1 style, the stuff that goes in compile is the stuff that you'd use when you're building your graph, and the stuff that goes to fit is stuff you'd pass to session.run?
Yes, that's correct. So let's move on to functional models. So in the previous example, you saw a subclass model. So essentially something that you wrote subclassing the model class. In practice, very often in the literature, you see deep learning models that look like this, that look like directed acyclic graphs. So on top you have inception V3, at the bottom you have various bits of a transformer. So these are directed acyclic graphs of layers that are connected with these arrows. So there's an API in Keras for configuring the connectivity of a directed acyclic graph of layers. It's called the functional API. It looks roughly like this. You start with input nodes, which are like these input objects. And then you're going to be calling layer instances on that object. So you can think of this inputs object as a spec describing a tensor. So it doesn't actually contain any data. It's just a spec specifying the shape of the input you're going to be expecting, the data type of the input you're going to be expecting, maybe you could also annotate with a name. And every time you call a layer, that's roughly the action of drawing an arrow from one layer instance to the next. So here you're going to have one input node, 2 layers, and here you're drawing an arrow from the input node to the first layer. Here you're drawing an arrow from previous layer to this new layer, and doing that for the output layer finally. And then you can instantiate a model by just specifying its inputs and its outputs. And what it's going to do when you do this is basically build this directed acyclic graph right here. So you can actually plot this graph. You can call utils.plot model on your model instance. It's going to generate this image. So a functional model is basically just like any other model, but it's just a model that you do not write yourself. So it has a bunch of methods that are auto-generated. In particular, the call method is auto-generated. The build method is auto-generated, and the serialization getConfig is also auto-generated. Yes?
The input does not have data, but could it have data? Like if you wanted to be able to check your work as you went along?
No, it could not. So when you define your model, you're not actually executing anything. You're just configuring a graph. So it's going to be running a bunch of checks, but they're only compatibility checks. So essentially checking that the layers that you're connecting together are compatible, that the data can actually be transmitted. But there's no execution. So there's no notion of data. It's really just an API for building a DAG. So yeah, so for instance, the call method is auto-generated. It's just going to be something that we call a graph of layer executor. So when you call your model, it's going to be basically running through this graph of layers, calling each layer in succession with the proper inputs. And likewise, assuming that each layer in your graph of layer implements this getConfig method, then you can call getConfig on your DAG and get something that you can use to reinstantiate the same model.
So excuse me, so on the, could you go back to muscle slice? So on the line y equals to model x, so that x is a layer or the input x?
X is the output of a layer. So you start by instantiating this inputs object using tf.Keras.input, which is basically a spec for a tensor, right? It has a...
The x here is different than the x above.
Oh, right. Yes, sorry. This is confusing. But yeah, this is supposed to be a tensor, like an eager tensor, for instance. Right, sorry, yeah. This is a bit confusing, sorry. Yeah, so you can call your model like you would call any other model instance or any function on a bit of data. It's going to return a bit of data. So what does the function API do roughly? Well, it's really an API for configuring DAGs. It's targeted more at users than developers, like people who are very comfortable with writing classes and functions in Python will have no issues using model subclassing to create new models. But when you want to use more like building APIs and you want more hand-holding, then the function API is actually a lot easier to use, and it maps very closely to how you think about your models if you're not a Python developer, because you think about your models typically like that in terms of DAGs, of layers. So it's declarative, meaning that you write no logic, you write no functions, you subclass nothing. It's really just configuration level. So all the logic that's going to be executed during when you actually call your model on some data is contained inside of layers. Typically, you don't write it. So that means that all debugging that happens when you build these models is done statically at construction time in terms of compatibility checks between layers. So that means that any functional model that you can instantiate without the framework yelling at you is a model that's going to run. So it means you don't write any actual Python code. You're just connecting nodes in a DAG, meaning you don't actually write bugs. The only kind of bugs you could be writing is misconfiguration of your DAG topology, which is what I call topology debugging, and that can be done visually by literally printing your graphs of layers and looking at how they're connected. On the technical side, these models can be expressed as static data structures that can generate code, that can generate a call method, meaning that they're inspectable. For instance, you can retrieve intermediate activations in your DAG and use them to build a new model. That's actually very useful when you do transfer learning, because it makes it very easy to do feature extraction. That means your models are also plottable. You can actually generate these little graphs, because you have a literal data structure underlying the model. And you can serialize them. When you have a subclass model, then your model topology is actually a bit of Python bytecode, which is harder to serialize. You have to pickle it. There's one very important restriction when you're writing layers that should be compatible with the functional API, which is that all the inputs of your layer should be contained in the first argument. Meaning that if you have multiple inputs, you should use list or tuple argument, or maybe dictionary argument if you have many inputs and they have names.
Tensor inputs.
Yes, tensor inputs. So essentially anything that comes from another layer. So like anything that you want to transfer using these arrows. Each arrow corresponds to the first argument in the call of a layer, right? So this is a restriction that also exists in Torch 7, right? In case you know. I know a lot of the people who have been criticizing this restriction are people who say Torch 7 is the pinnacle of deep learning API. So I think this is funny. Okay, so what actually happens when you build this functional model? Let's go in detail. When you instantiate this input object, it's basically this spec object as a shape and D type. When you create it, it also creates an input layer, which is basically a node in your graph of layers. And this input object is going to have an underscore Keras history field of metadata on it that tracks who created it, where it comes from. And every time you call a layer instance on one of these spec objects, what it's going to be doing is returning a new spec object, or nested structure spec objects with the inferred shape and D type corresponding to the computation that would normally be done by this layer. But in practice, no actual computation is happening when you do this. And this output has an updated underscore Keras history metadata that tracks the node that you've just created in your graph of layers. And finally, when you instantiate your model, from these inputs and outputs, we're going to recursively retrieve every node that has been created and check that they actually do form a valid DAG of layer calls.
So this Keras history field, does that have transitively a reference to all the layers that were?
So this is what it contains. It has, so it's basically, the Keras history is basically the coordinates of your tensor in a 3D space, discrete 3D space. It's basically a tuple, a name tuple, with 3 entries. So the first one is a reference to the layer that created this tensor, this spec. The second one is the node index, because layers can be called multiple times. So it's not true that there's actually one node associated with one layer. A node associated with a layer call. So if you call a layer instance multiple times, there's multiple nodes. So this node index is basically the index of the node created by the layer as referenced in layer._output nodes. And finally, there's the tensor index. So the tensor index is basically to handle the case of multi-output layers. If you have a layer with a bunch of tensor outputs, what we're going to do is deterministically flatten these outputs into a list and then index this list. And this tensor index tells you the index of this specific tensor among the various tensors returned by this layer call.
And if you take this y and then just call like tf.relu on it, it will still populate the Keras history and
not immediately. So the tf.nn.relu op is not going to create this Keras history object, but when this layer, this object is seen again by a layer, it's going to check, it's going to walk the graph and check whether it was originally coming from a layer, and if it does, then it's going to wrap the various ops that were not contained in layers. It's going to wrap them into new layers, so that you can actually step out of the Keras graph of layers and insert any TensorFlow up. And each TensorFlow up is going to be treated as its own node in the graph of layers.
So, two questions. One is, let's say that happened twice. Would there be two ReLU layers created, or would it?
Yes. So it's one layer per up.
It's the same node in the graph.
Yes. So one node corresponds to one call of a layer, right? So every time you call a layer, even if it's the same layer, that's a new node, because it has to be a DAG.
Okay, so I guess when you say ReLU creates a tensor, right?
Yeah.
And that tensor is then passed to another layer.
Yeah.
At that point, does it create a layer for the ReLU?
That's correct, yes.
So right then. And then if I were to pass that output of the ReLU to another layer, not the first layer, would it create another layer for that other ReLU, or would it reuse the?
I believe it does not recreate a layer, so it reuses the previous layer, but I would have to check.
Okay, this is all making me wonder about the lifetimes of all these layers? Is it possible? Is there references to all these layers just kept forever, or is that?
Yes, they are kept forever.
Layers are never garbage collected.
Yes. There's actually a utility in the backend to force destroy all of this. It's called a clear session.
Okay.
So this is to illustrate the importance of having these three coordinates. You can have, so this is some random variational autoencoder example I took from the internet. So it's interesting because it shows layers that have multiple inputs and multiple outputs. And like, for instance, the output of this layer are going to be going into, one of the outputs is going to be going into this other layer. One of the other outputs is going to be, going further downstream. So you can have, with these three coordinates, you can do, completely arbitrary graph topology like this. So there's a number of Keras features that are specific to these functional models, in particular, the ability to do static compatibility checks on the inputs of a layer, the ability to do whole model saving, meaning saving a file that enables you to reinstantiate the exact same Python objects with the same state, the ability to do model plotting, which is something we already just saw, automatic masking, which is something which we'll cover in detail, and dynamic layers, which is something that's not really relevant if you're not using the functional API. So let's talk about static type checking. When you create a custom layer, you can set an input underscore spec field on it, which is going to have to be an instance of this input spec object, or maybe a nested structure of input spec objects, which describe the expectations that the layer has with regard to what you should be calling it on. And when you call your layer for the first time here, you instantiate it here and you call it, first it's gonna check that this input is compatible with the current input spec, which was set here in the constructor, which just says the tensor should have at least rank 2. Then it's gonna actually build a layer. But here you see in this build method, the input shape that's passed here gives us more refined information about the expectations of the layer. So we update the input spec. So not only should it be a rank at least 2, the last axis, so axis -1, that's the last axis, should have exactly this value. So after you build, it's going to recheck that the updated input spec is compatible with this input. All right, that's the right last dimension. And finally, it's going to call. So every time you call a layer in the functional API to build these graphs, if the layer has set this input spec object, it's going to be checking compatibility and raising very detailed and helpful error messages in case of incompatibility. It's going to tell you what you passed, what was expected, and what you can do to fix it. You can also do whole model saving, meaning that you have this getConfig method that is auto-generated. You can use it to recreate the same model, in this case without the state. You can also just call save, and when you call load model, then this object is the exact same Python object pretty much with the same topology, the same state, and you can load it across platforms. For instance, you can also load it in TensorFlow.js. Yes?
If I write my own custom layer, do I need to do something special?
Absolutely. So if you want to write custom layers and reload your model in a completely different environment, that environment should have access to some implementation of your custom layer. So if it's a Python environment, then you basically just need to make sure the code is available, and you would wrap your load model call inside a scope where you specify the custom objects you want to be taken into account during the deserialization process. If you want to load your model in tf.JS, for instance, you would first have to write a JavaScript, TypeScript implementation of your layer. And yeah, model plotting, which is something we already saw, it's pretty useful when you want to check the correctness of the DAGs that you're building, unless they are too large, in which case it's not super interpretable. So this is just a very simple 2-input, 2-output model, 3-input, sorry, 2-output model where you have some title field, some body field, some tags field. You're doing some processing, and you end up with a priority prediction and a department prediction. So this is, just something from some random tutorial. And then one neat feature is automatic masking. So let's go over that in detail. Here's just a simple end-to-end example. You start from an input object that's going to be a variable length sequence of ints. It's called word sequence. So it's just going to be a sequence of word indices. You embed it with this embedding layer. And in the embedding layer, you specify a mask _ 0 equals true. So this layer is going to be generating a mask using 0 entries in any data you're going to be passing along this graph connection. And every time you call a layer that's compatible with masking, it's going to pass through this mask. And some layers, like the LSTM layer, are going to be mask consumers. So they're going to be looking at the mask that's passed and use it to ignore the padded entries. And some layers, for instance, if you have an LSTM layer that does not return sequences, that's just, basically just returns a single vector per sample, encoding the entire sequence, it's going to be destroying the mask. So the next layer is not going to see any mask. So when you do something like this, you're automatically telling the LSTM layer, which is significantly downstream from your embedding layer, to do the right thing with your sequences. So if you're not super familiar with the specifics of masking, this is very simple and magical. You just say mask 0 at the start of your model, and suddenly all the layers that should be aware of masking just do the right thing.
So a little more detail about what is masking? Is there a vector of Booleans or something?
Yes, absolutely. So here's the detail. A mask is indeed a vector, a tensor of Booleans. Each sample has its own mask, and each mask is it's basically just a plain vector of ones and zeros. It does not make assumptions about things like padding, for instance, so you could mask completely arbitrary time steps. Yeah, so you have 3 types of layers that interact with mask. You have layers that will consume a mask. So in order to consume a mask, just specify this mask argument in the code signature. And this will be your batch of Boolean vectors, right? You can also pass through a mask. There's almost nothing you need to do, but it's opt-in. You need to say explicitly this layer supports masking. The reason why this is opt-in is because many layers are going to be changing the shape of the inputs. So they're going to be returning outputs that are not the same shape as the inputs. And this interacts with masking. So it's typically not true to assume, for instance, here, it would typically be not true to assume that the mask that needs to be consumed by the LSTM layer is the same that was generated by the embedding layer. Well, in practice, it's the case. But if this dense layer had been doing anything to change the shape of the inputs, it would have been different. And then you have mask generating layers. So for instance, the embedding layer does something like this. It looks at the inputs and gives you a mask of Boolean entries that is 1 for all non-zero entries in your input. And in case you have a layer that modifies the shape of your inputs, it should also, if it wants to be compatible with masking, it should also implement this compute_mask method. For instance, if you have a concatenate layer that takes multiple inputs, some of which may be masked, some of which may not, the output mask should be the concatenation of the different masks.
So that compute mask method didn't use the mask argument, but normally you would.
Sorry, what? Yeah. Oh, yeah. So you can, yes. So for instance, the embedding layer is going to ignore the mask argument and just generate the mask based on inputs. But if instead you have a concatenate layer, it's going to ignore the inputs and just generate the mask based on the prior mask argument. So let's look in a lot of detail at how all of this is implemented. So what happens when you call a layer instance on a bunch of symbolic inputs? So the first thing we do is static type checking, determining whether all the inputs are compatible with this layer. If the layer is inbuilt, we're going to build it, potentially check input compatibility again in case the input spec was updated. We're going to check whether this layer is a mask consumer, like does it have a mask argument in its call method. If yes, we're going to retrieve the mask associated with the inputs of the layer, which we do via metadata. We're going to open a graph scope, check if our layer is graphable. So this is a concept we're going to look at in more detail afterwards. If the layer can be turned into a graph, we're going to autograph call automatically, and we're going to call this, so this is in order to convert if statements, for instance, or for loops into symbolic conditionals. We're going to call the call method that was autographed using the proper mask and turning argument that you retrieved from the current context. If the layer happens to be dynamic, meaning that you cannot convert it to a graph, you're just going to return a brand new symbolic tensors. And in order to know what shape and d-type these symbolic tensors should be, you're going to use the static shape inference method of your layer. Meaning that if you have a layer that's dynamic, that's non-graphable, and you want to use it in the functional API, it should implement this static shape inference method, compute output shape. For no other use case are you going to need compute output shape. So finally, you create the node in the graph of layers for this call. You set the metadata on the outputs, which are either these brand new symbolic tensors created using static shape inference, or the outputs of the actual graph mode call. So the metadata about the node. And finally, you set the mask metadata, which is what the next layer is going to retrieve in case that layer is a mask consumer.
So what's happening in step 5? What is the graph scope that you're talking about?
So Keras maintains its own graph, which is a fun graph object. And when it creates a symbolic tensor, it's always in that graph. So before you call the graph mode call, or before you instantiate new symbolic tensors, which are basically placeholders, first you need to open the graph scope.
Slight correction. It will enter that graph unless a different one has been specified.
Yes, which is only valid in V1. In V2, typically, you would only ever, like the only graph you're going to be manipulating is the Keras graph. Everything else, it's going to be either eager or a tf function. So we mentioned the notion of dynamic layers. So what's a dynamic layer? Well, maybe you remember this batch normalization example. There's actually something very subtle going on with this batch normalization example, which means that it cannot be turned into a static graph. And that is because, so it uses this if-else statement, and inside one of the branches, it does variable updates, and the other branch, it does not. And this actually does not play well with autograph. So this is actually something that's fairly easy to fix by simply having symmetrical conditional branches where you have the same statements assigning nothing in the other branch. However, for the sake of argument, let's say we cannot graph this layer. What are we going to do? Well, we're going to pass this dynamic equals true argument in the constructor. And that tells the framework that this layer is not compatible with graph execution, should never be executed in a graph. And when you build a functional API model using this, so it's going to do what we were mentioning in step 6. It's just going to use static shape inference to compute the outputs. When you call fit, it's going to be using pure eager execution without forcing you to specify a running girl equals true in compile. It's just automatically set to the right default.
So I think this one actually works because it should retrace for different values of training.
This?
This particular example should work in graph with.
Last time I checked, it would not work with autograph unless.
Training is a Python Boolean, but if it's a tensor, it's not.
Oh yeah, implicitly it's actually a tensor because so the reason why training is usually a tensor is because we use the same graph when you do fit and evaluate, and we change the value of training by fitting the value. So training is always symbolic. But yeah, you're right. If it's a Python Boolean, this works fine. In fact, autograph is not even relevant because the if statements are just going to be ignored by autograph.
What's the actual problem with control flow? I thought it was fine to have a stateful up on one side of a con.
It's that there isn't a corresponding output, and so they're like autograph can't match the function signatures.
Aren't those not outputs of each branch though? It would just be a stateful up in the. Oh, so it's like an API issue with con v2 or something.
Yes, it's a v2 issue. There's a long thread on this.
It's potentially fixable. It's potentially fixable. Anyway, this was just for the sake of example. There are also layers that are more fundamentally non-graphable, like a tree LSTM, for instance.
So that begs the second question of why is it important that you use the same graph for both fit and evaluate? Given that, for instance, in graph mode, the training versus inference flag, like in sort of the olden days, I think that was a Python Boolean, right?
Yes, that's correct. The reason why historically you had one graph for training and one graph for inference is because you would do inference on a separate machine that would load a checkpoint and run asynchronously compared to the main training. That's what we used to do at Google. In Keras, however, you're going to be running evaluation at the end of each epoch. So potentially you're going to be running evaluation very often, and you're going to be doing that on the same machine. So it's actually quite a bit more efficient to use a single graph to do this instead of keeping around two graphs.
If you have something and you call bash norm on it, that if they're in the same graph, for instance, you don't have to declare at that time whether you're doing training and inference. You can just have your tensor. You can do whatever you want downstream of it. Whereas if you have separate graphs, if you, for instance, output like a result in training mode and a result in inference mode, then the user has to track that, and it's not as pleasant.
Well, so there should be maybe different graphs that share all of their variables, right? Like different functions.
Yeah. Is this something that's like maybe an implementation detail that could?
It is very much an implementation detail. We could choose to generate a new graph when you do evaluation. Again, the reason this decision was made initially is really efficiencies, because two graphs is actually a lot of graphs. That's big. Even though the two graphs are almost entirely redundant, they only differ by a few counts for like dropout layer and bash norm layers. So we saw that having a symbolic training argument is actually much more efficient.